Hello everyone, my name is Thanasin Bunnam from Newcastle University. Today I would like to present my work toward designing thermally aware Memristance decoder. My supervisors are Ahmed Sultan, Daniel Sokolov, and Alexia Kopev from Newcastle University, UK, and Oleg Smevsky from Nano Devices, Russia. We have two motivations in this work. Let's start from the first one. Memristance is intensively used in many research areas, including edge computing. This enables AI computing such as neural network at the edge for a faster response and lower power loss due to communication between the devices and the cloud. Because Memristance is an analog device, we can read the data by using a Memristance decoder, which contains a comparator as the main building block. To improve the data density, we need a high-precision comparator, but this results in a longer latency and higher power consumption. Furthermore, edge devices are usually equipped with limited or unstable power sources such as batteries or energy harvesters. To survive under such conditions, the system must be able to trade its accuracy for the power saving. Therefore, designing a Memristance decoder with resolution scalability based on energy budget is one of our design challenges. This is our first motivation. For the second one, because Memristance is made from metal oxide materials such as titanium dioxide, which is temperature sensitive. But most Memristance models do not include the temperature effect. The temperature-enabled model usually contain differential equations which are able to cause a convergence problem in circuit simulation. Therefore, our second motivation is to create a simple temperature model of the Memristance to estimate the Memristance change over temperature. As a result, we can apply this model with our decoder circuit to enable a temperature sensor application. Note that our model can be used to compensate the temperature in memory application as well. Considering the temperature model, first we obtain the well-known Memristance model, where the total Memristance Rm is a portion of on and off Memristances are on and are off. This portion is defined by the state variable, which is Wt over d. This based on the assumption that the temperature impacts on R-on is very small and negligible comparing to R-off. We will consider the temperature effect on R-off only. Then, we replace R-off by a basic resistance equation, R equal to the resistivity rho times L over A. Next, the resistivity is expressed by an exponential relation, rho 0 times exponential of minus alpha times temperature T. We can simplify the exponential relation for lower computation load by using a second-order polynomial approximation C2t squared plus C1t plus C0. Finally, we obtain our model in a green block over here. Based on the data from the titanium dioxide memristors obtained from the literature below, we can fit our model using the coefficients C2, C1, and C0 as shown in the slide, with the maximum error of 1.25%. Using our model and the obtained parameters, we can plot the IV curves at different temperatures from 25 degrees Celsius to 125 degrees Celsius in the picture. We can see the highest R-off is at 25 degrees Celsius in the blue plot. This is because the blue plot looks flat around 0 milliamps. The slope is the steepest at 125 degrees Celsius in the red plot, where R-off is the lowest value. Here we consider the temperature effect in multi-bit memory application using our model. In this case, we split 2-bit data into 4 sections across the entire Memristance range. For example, at 25 degrees Celsius, the top section is data 00, which is between 230 kilo ohm and 330 kilo ohms. And the below section is for data 01, which is between 160 kilo ohm and 230 kilo ohm, and so on. Suppose that initially our Memristance is programmed as 200 kilo ohms at 25 degrees Celsius, which is data 01, representing by the red dotted line. When the temperature rises to 40 degrees Celsius, the Memristance range is narrower, and the program 200 kilo ohms is shifted to the new value, which is 140 kilo ohms. If there is no temperature compensation, the decoder will read the value based on the old range, which is 25 degrees Celsius, where 140 kilo ohm is data 10, not 01, as we programmed before. We can see the reading result would be worse when the temperature keeps rising to 65 degrees Celsius and so on, because the data section is very close to each other. Therefore, we strongly need a compensation circuit or compensation technique for memory application. Now, we are going to show our decoder design, which consists of a controller and a resistant comparator, which is inside the dashboard. Note that this work focuses only on the comparator. The controller implementation will be our future work. The comparator consists of 6 subcircuits: current mirror A, B, and C, a digitally controlled current source, TCAS, which is our reference source, a regenerative latch, and a metastability resolver, MSR. The current mirror A is the place where our Memristance is integrated to our decoder. The comparator is controlled by EN and CMP signals, which are stated in the top right table over here. We will talk about them in the next slide. The idea of the comparator is to feed the Memristance current from the current mirror A and the reference current from TCAS to the latch. Both current will against each other in the latch. Then its output will be sent to the MSR to filter the metastable state. Next, the controller reads the output greater than or less than, which are listed in the table over here. Note that greater than or GT means the Memristance current is greater than the reference current, or the Memristance is lower than the reference one. And less than means the Memristance current is less than the reference current, or the Memristance is larger than the reference one. Finally, the controller adjusts the reference current in the TCAS block depending on the search algorithm and the available energy. Here is our circuit design. Regarding the operation mode over here, when there is no need for decoding, the controller will set EN as 0 to turn off PM6 and the blew-up transistor of the TCAS to stop the current flow and save the power. The decoding process starts by setting EN to 1 and CMP to 0. This will turn on all subcircuits to let the Memristance and different currents pass through the latch over here. Next, the CMP signal is set as 1. This is to turn off NM2 and MM3 to let the latch resolve the output. Note that we added two capacitors, CM and CF, to represent the capacitor arrays for offset calibration. We will talk about this in the later slide. To demonstrate the cumulative operation in 2-bit memory application, we define about 80 kilo ohm range for each data. This can be done by changing the size of the transistor in current mirror in the TCAS circuit. The memristance range are listed in the table. The number shown in the table specify the upper bound of the range. For example, the range for data 00 is from about 237 kilo ohms to 325 kilo ohms. Note that the data range for data 11 is narrower than the other because turning on multiple current mirrors in the same time decreases the path resistance and increases the current. The range in the previous slide are defined based on DC current, but there are switching activities from the control signals EN and CMP which cause the effect from parasitic capacitances. This results in the different memristance ranges as listed in the third column. We ran a Monte Carlo simulation with 209 samples to see a mismatch regarding process variation and the use of the capacitor array to calibrate this offset. The TCAS is configured to equivalent the memristance of 324 kilo ohms, which is the upper bound of data 00. We found in most samples the rated memristances are between 0 and 800 kilo ohms, which is very far from the initial value. We took the worst sample that was read as 0 ohms. In the bottom graph, we found adding 10 femtofarad capacitor at CF can resolve this extreme mismatch as the output start toggle between LT and GT. In comparing our work to the literature, our comparator has a latency of about 3 nanoseconds, which is higher than the other current mode dynamic comparators, but it has a lower power consumption of about 20 microwatts. The advantages over the literature are that our comparator is designed for memristor application because we have already included the memristor interface. We also improve the resolution scalability to be able to decode the memristance depending on the energy budget. Moreover, there is no resistor, which is also highly temperature sensitive in our design. Coupling our temperature model with our decoder design for the sensing application and investigating the self-temperature compensation technique are subjects for our future work. Thank you for attending my talk. Please drop me an email if you have any questions. I am happy to reply and discuss.